Okay, it looks like we're at a great number here. So let's kick it off. So before we get started, first I'd like to introduce myself. I'm Deep Ganguly. I'm the Director of Research at the Stanford Institute for Human-Centered Artificial Intelligence. And I want to start off with some house rules. So the chat is disabled for the duration of this event. If you have questions for the speaker, please use the Slido application. So you can find that by pointing your mobile device at this QR code, or you can go to the HAI events site, and there should be a prominent link to join the conversation. I will be monitoring those questions throughout and asking Serena those questions at the end of the seminar. And we will repeatedly sort of give you the link in the chat on this Zoom screen as well. And now I'd like to introduce you to Professor Serena Yeung. Super excited to have her here today. Serena is an assistant professor of biomedical data science and by courtesy of computer science and electrical engineering at Stanford University. Her research interests are in the areas of computer vision, machine learning, and deep learning, focusing on applications to healthcare. She also serves as the Associate Director of Data Science for the Stanford Center for Artificial Intelligence in Medicine and Imaging, and is affiliated with the Stanford Clinical Excellence Research Center. I should also interject, these are close friends and family to HAI. And then prior to joining Stanford faculty in 2019, Serena was a Technology for Equitable and Accessible Medicine postdoctoral fellow at Harvard University, where she was hosted by Susan Murphy and John Halmaka. Serena received her PhD from Stanford in 2018, where she was advised by Fei-Fei Li and Arnold Milstein. And during her PhD, she also spent time at Facebook AI Research in 2016 and Google Cloud AI in 2017. And without further ado, I will hand it over to you, Serena, and I'll see you at the end.
Okay, thanks, Steve, for the introduction. Let me just share my screen here. Okay, so hopefully you can all see my slides now. And in my talk today, what I'd like to do is to explore the potential role of AI as a partner to clinicians and its capacity to augment clinician capabilities across a spectrum of healthcare use cases. And in particular, we'll consider the respective strengths of AI and humans and the different ways in which they can complement each other in diverse settings. So I want to start by zooming out and talking about an environment where large parts of healthcare take place, and those are hospitals. Hospitals are environments of highly complex care. And as doctors and nurses perform their day-to-day work treating patients, burnout has unfortunately become a new normal. 78% of physicians and 62% of nurses experience feelings of burnout. This is dangerous. Studies have reported that burned out doctors are 2 times more likely to make medical errors, and overworked nurses are associated with a 40% increase in the risk of patient death. And this is all pre-pandemic. If we consider situations such as the current COVID pandemic, where healthcare workers are presented with significant new challenges, such as additional protocols and safety precautions, and not to mention overloads of patients in hospitals, well, everything just gets worse. Now, if we take a step back and we think about other industries such as driving, AI has long been recognized for its potential to provide constant awareness and assistance to humans, including in situations where humans are susceptible to fatigue. And so this naturally leads to this question in medicine of, can AI also provide useful assistance to physicians and nurses? And what precisely should the nature of this partnership be? Well, the degree of AI assistance to humans can occur over a spectrum. In autonomous driving, for example, this has been categorized as different levels of autonomy, ranging from level 0, where humans have full control, to level 5, where the AI has full control. And in the middle, there are different paradigms, such as the AI providing useful information, but the human driving the action, to the AI driving the action and humans stepping in as needed. And for many efforts in autonomous driving, the holy grail is full AI autonomy, although current embodiments target various levels on the spectrum. So in healthcare, there can be many different types of AI applications that have different needs, where the ideal type of collaboration may lie at different levels on the spectrum. But I'd argue that for most applications, at least in the realistic future, what we'd like is not full human control or full AI control, but a true partnership that falls somewhere along levels 1 to 4 on the spectrum. So how can we think about the use cases where AI can have the most benefit in healthcare and what the nature of the AI and clinician partnership should look like? Well, let's start by thinking about the inherent strengths of AI versus humans. As a first comparison, modern AI algorithms, and particularly those based on deep learning, have shown themselves to be excellent and sometimes even superhuman at pattern recognition. However, they still generally lack the logical and knowledge-based reasoning that humans naturally perform. For example, current AI algorithms would still struggle at reading a story and answering logical questions about the events. As a second comparison, AI also has the ability to access and store vast amounts of data far beyond what humans are capable of. And they can utilize this in practical applications, for example, by retrieving cases that are most similar to the current one. But on the other hand, when there are special cases that require special considerations or fall out of the training data distribution, then AI algorithms can fail catastrophically, whereas humans can still apply their reasoning to be able to perform reasonably. Thirdly, AI is a wonderful automator. Once it has learned how to perform a task, it can perform the same task over and over again without fail and without getting bored. Humans, on the other hand, often don't enjoy as much performing the rote tasks that are most easily automated. They prefer to spend their time on more stimulating tasks, such as those requiring creativity and improvisation, and on which they typically also surpass AI algorithms that are hampered by their data-driven nature. And finally, while in some cases we're happy to rely on tireless algorithms that don't fatigue, there's still many moments, and particularly vulnerable moments, that we might experience during healthcare crises, where I think many people would still prefer genuine human empathy from their doctors and nurses. So we've talked a bit about the strengths and weaknesses of AI versus humans. And with this in mind, in the rest of this talk, I'd like to look at a sampling of use cases in healthcare across the spectrum, from clinical procedures to hospital monitoring and telemedicine at home. And I'd like to talk about some of the different applications of AI and clinician partnership that my group is excited about, and our ongoing work in developing the AI capabilities towards these applications. I'll start first with the clinical procedures that clinicians perform, often in acute settings, and I'd like to focus in particular on surgery. Surgery is one of the major operations in hospitals. It has the potential to cure many diseases, but it's also a challenging environment that requires a high degree of skill. Postoperative mortality has been reported as the third leading cause of death worldwide, and studies have shown that surgical technique during operations has a significant effect on patient outcome. So how might we be able to use AI to augment surgeons during these critically important times during procedures? Well, video can capture a lot of information about what's happening during surgeries, and it turns out that surgeons are sometimes already capturing video data. For example, laparoscopic surgeries are video-based and already produce a video stream. And for traditional open surgeries, surgeons sometimes capture video through head-mounted or overhead-mounted cameras. And one reason for this is actually for reviewing and studying surgical technique. And so this highlights the value of the information that is in the surgical video data. And so it naturally follows that developing AI, which can automatically recognize and interpret what's happening in surgical videos, could be highly valuable for surgeons. As an example of two major application areas, one use case can be providing assessment and feedback on surgical skill for training purposes. And another use case is providing real-time situational awareness, an AI that could interpret what's happening in the surgery and compare this with thousands of other videos on which it's been exposed to during training could be useful for providing feedback on decision-making and risks. Both of these applications leverage the strengths of AI. In the training application, we need to use pattern recognition to recognize what's happening in the surgery. And we also leverage the automation benefits of AI. Expert surgeons can provide feedback to less experienced surgeons, but they don't have the same time capacity as an AI does. For the second application on real-time situational awareness, we again need pattern recognition to recognize what's happening in the surgery. And importantly, we can also leverage AI's search and retrieval capabilities to compare the situation in the current surgery with many others. However, with so many variables and factors at stake, there may be reasons for a surgeon to want to perform a surgery in a certain way. And so surgeons are still the ultimate decision maker and operator and can consider AI data-driven support together with their own reasoning. We can see this type of partnership in some ways as stages 1 to 2, where the surgeon is in control, but the AI is providing assistance to the surgeon. And so in our lab, we've been excited by these possibilities of AI and surgery, and we've been working towards developing algorithms for AI-based surgical video analysis. The first type of surgeries that we targeted were laparoscopic surgery videos. These surgeries are video-based, where surgeons insert a tiny camera and tools through small incisions into the body. And since the field of view consists primarily of tools manipulating body tissue, we started by developing a deep learning-based algorithm to perform object detection of tools in the video. And so here you can see examples of tools being detected in a sample video. Now, once we have the tool detections, we can produce analytics of tool usage over time to gain insight into surgeon technique. So here I've shown 4 example videos, 1 in each column. And in the first row, I'm showing the presence of different tools detected over time. The second row shows spatial heat maps of tool locations over time. And the third row shows more detailed tool trajectories during a specific portion of the surgery. Now, if we compute some statistics based on the detections, we can see that here on the left, we have the total time that each instrument is used in each of the videos, and on the right, the total distance that's traveled by the instruments. And these statistics can provide some interesting information. For example, video 3 has a higher usage of the bipolar instrument, which is used to stop bleeding, and so this can be an indication of tissue damage. On the other hand, on the right, we can see that video 2 is the most economical in terms of motion, which is a characteristic that's usually correlated with higher skill. Now for these videos, we also had 3 surgeons manually watch and rate each of the videos using the GOLS ratings for laparoscopic surgery, which is an established scale for laparoscopic surgery skill. And we can see that the surgeons rated video 2 to have the highest skill and video 3 to have the lowest skill, which is consistent with some of the insight that we gleaned earlier. And while this was a small study, I think it demonstrates the promise of AI-based surgical video analysis, and we're now scaling this work to a larger scale. Now, laparoscopic surgery is great because it's already video-based, but open surgeries still comprise the majority of surgeries. We can imagine that AI is likely very useful for analyzing open surgeries as well. However, this setting is significantly more challenging. So first of all, open surgery videos can be collected in much more diverse settings with different viewpoints, such as head-worn and overhead-mounted cameras, as well as with larger fields of view showing surgeon hands, anatomy, and other elements of a surgery scene. And so most existing work on analyzing open surgery so far have therefore relied on non-visual sensors such as motion tracking sensors. And finally, since data capture is much less standardized here than for laparoscopic surgeries, they currently lack datasets to support the development of AI algorithm. So faced with these challenges, we turned to a resource that seemed interesting to explore, and that was YouTube. There's so many videos of all kinds of things now on YouTube that we thought, well, how often might surgeons be posting videos of surgeries on YouTube? And well, it turns out that it's actually quite often, and YouTube is actually quite a rich and active repository of surgery videos. And so in work that was led by our group members shown here, Emmett, Krishna, Michael, Stephen, and Rohan, as well as our collaborators at Harvard and Beth Israel Deaconess Medical Center, led by Dr. Gabriel Bratt, we proceeded with a methodical scraping of thousands of surgery videos under several major categories: breast, gastrointestinal, and head and neck surgeries. And here you can see a word cloud showing some of the popular types of surgeries that appear in our data set. Once we obtained this data set, we turned to developing computer vision algorithms to recognize various aspects of the surgical scene, and we also annotated the data set to support this algorithm development. And specifically, we targeted first the temporal detection of several common surgical actions: cutting, tying, and suturing. And we also targeted detecting hand locations and hand poses based on the key points shown here. And then finally, we targeted also detecting several major tools, the Bovie, needle driver, and forceps. Now, to obtain an AI algorithm that could take a video as input and simultaneously produce a rich set of outputs, both effectively and efficiently, we developed a multitask deep learning model. Our model is composed of a shared backbone of neural network layers to extract useful lower level features, as well as task-specific heads that reason on top of these features to output action and hand and tool detections. And so in the end, we were able to train a model that could perform simultaneous recognition of actions, hands, and tools in the surgical scene at real-time speed. Here's an example showing an early version of our model in action, where here you can see the detected hands and key points inside the green boxes, the tools in the blue boxes, and action detections in the moving bar at the bottom. And now with this model, we're again able to obtain detailed characterizations of videos. So for example, we can plot the sequence of actions occurring in a video. I've shown this here for 30 appendectomy videos, and we can start to see broad patterns occurring with lots of cutting in the first part of the surgery, followed by suturing and tying later on. And we can also average these to obtain the prototypical structure of an appendectomy, just shown here on the right. Now, if we look at action distributions across different types of surgeries, we can see clear distinctions between them. And we can also add the same type of information about the structure of tool usage to get even more information. And if we generate feature vectors from the actions and tool usage of each video and cluster these features, the videos naturally organize into distinct groupings based on their surgical type. And finally, as we did with the tools in laparoscopic surgery, we can also analyze movement. So here I'm showing the movements of hands over a period of time overlaid on the surgical video. And we've used blue to indicate slower and steadier motion and red to indicate faster motion. And in this example, you can see that the surgeon on the left has an overall steadier trajectory, which is a characteristic of higher skill, while the surgeon on the right has a wider distribution of velocities, including larger jerks, which is a characteristic of lower skill. And so I hope this illustrates some of the interpretation and analysis of surgical videos that's possible using AI. And finally, one other key component that we'd like in AI analysis of surgical videos is recognition and in particular segmentation of anatomical structures. As we work towards applications for real-time situational awareness, anatomy will be critical for situating actions and providing context-aware assistance, such as warning that you might be at risk for injuring a particular anatomy. And for the next 2 or 3 slides, if surgery makes you queasy, you might want to just look away briefly. But in a project that was led by my student Julia Gong and our collaborator Chris Holzinger at Stanford Medicine, we're developing computer vision to be able to segment an important tissue, the recurrent laryngeal nerve, in thyroidectomy surgeries. And this is a critical soft tissue that's important not to damage, and so we want to be able to identify it. To approach this problem, we first collected a data set of digital camera images containing the nerve from diverse conditions, including different lighting conditions and different levels of zoom. And we then developed a segmentation model that first involved automated detection and pre-processing of the wound image to be able to obtain standardized images that are robust image capture conditions. And then we trained a UNet-based model to predict the output mask of the nerve. In addition to this, one really useful aspect of AI-based interpretation is that it can also provide richer interpretations, such as not just recognizing the nerve, but also producing automated measurements of the nerve. And in this case, since the retractor tool in the surgeries has a standard known size, we can actually use AI to detect both the nerve as well as the retractor tool, and then calibrate their relative widths to estimate the width of the nerve. So after developing this approach, we evaluated our model, and we were particularly interested in evaluating it with respect to different camera settings, since this is important for designing deployments in real-world application. And what we found was that we could achieve an overall strong performance across diverse settings, but if we optimize the camera capture to ideal conditions, then we can get the highest performance overall. And finally, here are some examples of estimated nerve width based on the predicted nerve segmentations that are boxed in red, and the predicted retractor segmentations that are boxed in green. Okay, so I've discussed some of our ongoing work on developing AI to augment surgeons during procedures in the operating room. And next, I'd like to move to a wider view of healthcare, of using AI to enhance clinicians, not just during specific procedures, but also the entire hospital stays of patients. And I'd like to talk in particular about some of our work on developing ambient intelligence using visual sensors to augment clinician capabilities to monitor human activities in the hospital activities and patient care beyond what's currently possible with human effort. So what exactly is ambient intelligence? Well, the term of ambient intelligence broadly refers to building continuously perceptive and responsive physical spaces. And in an environment like a hospital, we can see ambient intelligence as provided through visual sensors that are embedded in the environment and that can perceive and interpret what's happening across the hospital at every moment in time and use that to assist with clinical care. Ambient intelligence could be a constantly aware and untiring assistant that can be used as part of systems that provide real-time assistance, and particularly to overburden physicians and nurses to perform tasks such as ensuring protocol compliance, monitoring patient status when no one is at the bedside, providing automated documentation of patient care activities, and much more. Now, referring back to our discussion on AI and human strengths, the types of ambient intelligence use cases that I've just mentioned all require pattern recognition to recognize events from visual sensor streams. But on top of this, they particularly leverage AI's strength of automating rote tasks, such as monitoring and documentation, and its ability to perform these in a continuous and untiring fashion. So one thing that I want to highlight here is that while the surgical assistance that we discussed earlier is an example of using AI to help clinicians achieve higher performance at something that they're already doing, the ambient intelligence applications here instead scale clinicians' capabilities to what they're not yet able to do or do not want to use their time to do. Over the course of patient hospital stays, ambient intelligence could perform these important yet rote tasks and free up more of clinicians' time for decision-making and having meaningful interactions with patients. The forms of AI and clinician partnership here are therefore typically ones where the AI and clinician perform complementary and different activities. The AI in performing ambient intelligence tasks is typically in the driver's seat, constantly monitoring hospital activities without human supervision, and instead it alerts clinicians when an intervention is needed. So grounded in this vision of ambient intelligence that I've described, in our work, we've implemented ambient intelligence sensing in practice at 2 partner hospitals, at Lucille Packard Children's Hospital at Stanford and Intermountain LDS Hospital in Utah. And at each of these, we've equipped a pilot hospital unit with about 50 visual sensors in both patient rooms and corridors. In these initial implementations, we chose to use depth sensors for the ambient sensing because they collect these silhouette-like images that are based on distance to the sensor and that provide informative visual data, but at the same time provide simpler privacy preservation by their very nature. These photos on the left show examples of depth sensors mounted in our pilot installations, and on the right is an example of depth image data, where here darker means closer to the sensor. So now once the visual sensing is set up, the main technical challenge is to actually interpret what's happening in the video data. So in our work, we've focused on developing deep learning algorithms to accurately recognize human activity occurring in video, although I won't go into detail on these for the moment. We've now demonstrated the use of our first algorithms to be able to continuously monitor 24/7 a variety of health critical activities in the hospital. One example is monitoring hand hygiene, which is something that I'm sure we're all much too aware of in the current COVID pandemic. But on top of that, hand hygiene has always been an important activity to prevent hospital-acquired infections. So we developed an algorithm to predict hand hygiene events. And here on the top, I've shown a 2-hour time window from one hospital unit, where in the 4th row, you can see the hand hygiene events detected by the algorithm. And what we found was that our AI algorithm performs very closely to the ground truth in the bottom row. And more importantly, in a comparison with in-person auditors, which is the current standard, it took 4 more human observers positioned across the unit to match the performance of the algorithm. Next, in order to assess hand hygiene compliance, or whether people are performing hand hygiene when they should be, we need to understand the movement of people around the unit. And so we developed an algorithm that produces tracks of human movement that looks something like this, where here you can see people entering and exiting rooms. And then now putting everything together, we can tag a person as having been compliant due to the use of the dispenser right here before entering the patient room, or as non-compliant. A second use of ambient intelligence that we've also prototyped is monitoring patient mobilization activities in the ICU. And these are activities such as getting a patient in and out of bed and transferring them to and from a chair. And these types of early patient mobilization is important for preventing complications such as ICU-acquired weakness, pressure ulcers, and prolonged hospital stay. So we developed an algorithm that could recognize these activities from depth sensor video. And here on the top, you can see an example of our algorithm predicting the time occurrence and duration of each mobilization activity. And in this video, see if I can play this again, you can see the algorithm detecting the patient getting moved out of the bed and now being transferred to a chair, right? And then they're going to get moved back into the bed and so on. And so one thing that I want to point out here is that because of AI's ability to perform detailed pattern recognition at scale, here by using AI, we can easily record not just the fact that these activities happened, but also other characteristics like how long they took or how many people were involved. This is beyond what humans would practically be able to do, but it can be valuable for additional uses, such as designing care guidelines and resource optimization. Okay, now what I've talked about so far is ambient intelligence using depth sensors, but we can also develop ambient intelligence using standard RGB or color sensors. RGB video inherently contains more appearance detail than depth video, and so it's typically appropriate in settings either where less privacy protection is needed or where there are additional privacy protecting mechanisms that are possible, such as edge computing or blurring. However, when RGB sensing is possible, it can also provide a number of advantages. The sensors are typically cheaper and more lightweight than depth sensors, and the additional appearance detail can enable more ambient intelligence applications. Importantly, there's also an additional technical challenge, which is that color images do not directly provide 3D information, which is often useful for precise understanding of how humans interact with their environment as well as with each other. And so in some of our recent work, we've been tackling this key technical question of can humans attain a 3D understanding, can algorithms attain a 3D understanding of human behavior and interaction with the scene from only 2D images? This is work that is led by my student, Jen Wang, and we've developed an approach that takes 2D images as input and estimates the 3D scene structure with 3D human and object meshes. Since it can be challenging to perform estimation in crowded scenes where humans and objects might be partially occluded, our approach introduces a holistic reasoning process over the entire scene, such that each component of the scene provides useful plausibility cues for other components. So specifically at a high level, given a 2D image, our method first performs 2D detection of human body pose and object bounding boxes in the scene. We then use independent neural network modules that ensure consistency between 3D structures and their 2D reprojections to obtain initial 3D estimates of major scene components. And these are the 3D object bounding boxes and their corresponding 3D object meshes, 3D human meshes, and the 3D room layout. The outputs of these 3D estimation networks are then refined through 2 stages of holistic reasoning losses. The first stage is comprised of within scene and within body losses that encourage the human body, as well as everything other than the human body, which here we call the scene, to be physically plausible. So for example, the human reprojection error to 2D should be minimized while considering that some body poses are more likely than others. And object reprojection error should also be minimized while considering that objects should not intersect with each other. Then in a second stage of optimization, we encourage human interaction with the scene to be physically plausible. So for example, humans should not be able to penetrate the floor or intersect through objects. Now, after these two stages of optimization to refine the initial estimates and the initial 3D estimates with holistic reasoning, we can then obtain the final estimate of the room layout and the humans and objects in it at a mesh level. We've evaluated our algorithm on some computer vision benchmark data sets where ground truth is known. And here you can see some examples showing the improvement from the initial mesh estimates of each image in the center column to the final estimates on the right after the holistic optimization. And we're now also investigating the application of this algorithm to image data from hospital environments that represents the kind of data that might be captured by RGB ambient sensing. So I've shown here an early example of our algorithm applied to this ICU image on the left. And on the right, you can see that the algorithm accurately reconstructs the precise 3D positions of the humans and their interaction around the patient bed. So as we continue to work on this 3D estimation from 2D images, another complementary question that we're simultaneously studying is, how can we efficiently scale the number of objects that our AI recognizes? In other words, how can we teach the AI about objects of interest in any given application or scene without having to label many examples of the object, as is the current paradigm for supervised learning? This is a challenging problem, and so we've started by investigating this in the 2D setting. Specifically, we formulated our goal to be developing a model that, given a set of images, can learn to quote unquote discover the distinct object categories in them and output the masks or segmentations of each object across all the images with minimal human input. And we particularly want the model to be quite comprehensive in its discovery of objects, specifically extending to the long tail of categories, since these are likely the ones that we would least want to manually annotate training data for. This is work that's been led by my students, Jen, Hirai, and Shai. And the high level of our approach is as follows. We first observed that for current state-of-the-art segmentation architectures, such as MASC RCNN, if we take the region proposal network of a MASC RCNN, we actually get a pretty good mask proposal generator that picks out our distinct object masks in the scene, but all without a category label. And this is the case if we train the region proposal network in a class agnostic way. And so that's why it's predicting these category agnostic masks. And so now if we use that, the main technical challenge becomes, how can we learn good feature representations of the regions corresponding to each of these masks, such that when we cluster them, they'll naturally organize into distinct object clusters. And so in our approach, we perform representation learning of the masked regions using a set of self-supervised losses based on the hierarchical structure of the images, where many objects are nested in other objects. We introduced a foreground background loss that encourages masked regions to have distinct representation from their background, which would likely be a different object. We also use an intersecting objects loss such that overlapping objects, which are likely related, have a more similar representation than a faraway object. And finally, we introduce what we call the hierarchical loss, where when one mask is fully contained inside another, such that there's a parent-child relationship, we encourage the respective representations to be close to a corresponding approximate tree relationship in the hyperbolic embedding space. And so finally, once we've learned feature representations corresponding to each mask, we can then cluster these representations to obtain groupings of masks. And a human can then inspect each cluster and simply assign it a category label, which is much more efficient than generating a training data set of object segmentations. And so using this full pipeline, we can obtain instant segmentations of fine-grained categories. Now, in order to validate our proposed method, we used a computer vision benchmark dataset called ELVIS that did put in the manual effort to densely annotate masks of 1,200 object categories in a dataset of daily life images. And we found that our approach was able to discover and segment categories in the long tail with significantly higher performance than other works that have used limited human labeling. So I've shown here some qualitative examples where on the left are some of the segmentations output by our model, and on the right are masked regions corresponding to some of the discovered object clusters. And while some of these clusters have corresponding class names in ELVIS, we found that in some cases, we also discovered additional novel categories with no corresponding label in Elvis, such as the toggle switch in the bottom row. Now, similar to the 3D reasoning model that I discussed previously, we're now also investigating the application of this method to image data from hospital environments. And I've shown here an example of some of the object masks produced by our model on an example ICU image. And you can see that it's already capturing quite fine-grained objects, where here different colors correspond to different object clusters. Okay, so in this part of the talk, I discussed our ongoing work on developing AI towards ambient intelligence applications. It's based on a continual perception of what's happening in hospital environments. And finally, in this the last part of this talk, I'd like to zoom out to an even broader lens of healthcare, and that's extension beyond traditional healthcare delivery settings, such as hospitals, to the home setting. And in particular, I'd like to talk briefly about telemedicine, which is a relatively new form of healthcare that's just beginning to explode, and where I think there are currently exciting opportunities to design the role of AI in telemedicine. So while the use of telemedicine has been growing in recent years, the COVID pandemic has catalyzed an almost overnight explosion in the use of remote care and telehealth applications. Since the pandemic, there's been a more than 100% increase in virtual urgent care visits and a more than 4,000% increase in virtual non-urgent care visits, according to some studies. On the right, I'm also showing data of the number of video visits per month that Stanford Children's Health has publicly provided pre and post-pandemic. And you can see the dramatic increase starting in March and April of 2020 of video visits. There's a growing ecosystem of diverse digital health platforms and telehealth applications that range from video visits to text-based chats. And while AI-powered telemedicine is still really in its infancy, the range of telemedicine applications is so large that we can imagine the AI and clinician partnership taking a range of forms. For example, we can imagine applications in the levels 1 to 2 range of autonomy, where clinicians are in the driver's seat for telemedicine visits, but the AI functions in an assistive background capacity to perform roles such as documenting symptoms or suggesting diagnoses. On the other hand, in other applications, AI could be the main point of contact for the patient, such as an AI-only visit for screening purposes or informal question answering, and clinicians may intervene only when the AI is unable to perform the task due to abnormal visit conditions or difficult corner cases. The various uses of AI in telemedicine leverage many of the AI strengths that we've talked about. And that's whether it's using data to help enhance clinician performance during telemedicine visits that they're already performing, or on the other hand, whether the AI is operating more autonomously to provide patients with additional touch points and interaction with the healthcare system beyond what clinicians have the time to provide. But in all cases, AI can enable clinicians to focus on the most important and meaningful parts of patient visits. So our lab has ongoing work on developing AI capabilities for telemedicine across both video and text-based applications. But today I'd like to briefly highlight one particular research project that we've worked on, which is AI algorithms for automated history taking in chat-based telemedicine. This project has been led by my student Ali Motagi and in collaboration with the telehealth company Curii. And in particular, we focused on one common component of virtual visits, which is a patient describing why they're seeking help, or more formally, their reason for encounter, or acronym RFE. An automated history-taking algorithm needs to extract the patient's presenting symptoms from their RFE text, but this is non-trivial since patients often type in quite a colloquial manner. This is where machine learning comes in, where given a training data set of RFEs, and their corresponding clinical symptom categories that are labeled by clinicians, we can use supervised learning approaches to train a model for producing a list of presenting symptoms from an RFE. A particular challenge in this setting, however, is the fact that some symptoms are much more common than others, and multiple symptoms can be present in any RFE, which leads to a long-tail distribution of data corresponding to the space of possible symptoms. And so as a result, random brute force labeling of data until there's enough data for each symptom is highly inefficient and would be very expensive. So to address this challenge, we proposed an active learning approach to data labeling, where instead of brute force labeling a large data set for training, we can train a label acquisition function in conjunction with the target classifier. And the label acquisition function can iteratively request much smaller sets of labels from experts for what the algorithm anticipates should be the most informative examples. And so in particular, we introduced an active learning approach tailored for long-tail distributions, which we call active long-tail learning. To determine which specific examples to label, we first extract the feature representation of each RFE based on infraset sentence embeddings. And we start with a small number of labeled RFEs. And then we repeat an iterative process where we first perform clustering in the embedding space using the affinity propagation algorithm to obtain underlying structure that could correspond to different semantic categories. We then perform an optimization process to select a batch of examples for labeling that balances both current state-of-the-art active learning objectives of being spread out over the latent space, together with the second objective of having increasing density near latent cluster centroids, since it's particularly difficult to learn the representation of rare long-tailed categories. Now, once human experts provide labels for the selected examples, we can use these to update the classifier, as well as refine the clustering in the latent space and repeat the process from there. And we can continue the active learning process until we've exhausted our labeling budget or the model's performance is satisfactory. So we've evaluated our method for active learning of RFEs using a data set of 1,000 RFEs from the CureAI platform that were known to contain 20 different symptoms distributed in a long tail manner. The curves on this plot show the classifier performance of different models as more data is labeled from left to right. All the methods here start with a small set of 10 labeled RFEs, and then they can incrementally request labels for batches of 10 more RFEs at a time. Our method is shown in blue, and it's able to achieve higher performance than previous state-of-the-art methods for active learning. And here, the purple line serves as a reference for when the labels of all examples are used. So now, given these promising results, a next step would be to start exploring the deployment of the algorithm at larger scale in the wild. So this is an example of some of the technical challenges that we're tackling as we develop AI for emerging health technologies such as telemedicine. And now here, I want to also take a moment to highlight that as we develop these new technologies, which bring with them new types of healthcare data and new applications, that this often also requires new considerations about ethics and other social implications. And it's important to think about these issues from the beginning to be able to better guide the development of this technology. So in our work on ambient intelligence, we began to think about questions such as privacy and re-identification risk, consent and liability in collaboration with the Harvard Petrie Flum Center for Health Policy and Ethics, led by Professor Glenn Cohen. But in both this technology, as well as other new technologies such as telemedicine, there remain still many questions still to be even raised, as well as answered around issues such as bias, fairness, health disparities, and other social impact. So to summarize, in my talk today, I've discussed AI applications, and in particular, AI and clinician collaboration across a spectrum of healthcare settings, ranging from surgical procedures to continuous hospital monitoring, and finally telemedicine at home. And in each of these, I presented some of our ongoing work in developing the AI capabilities that are needed for augmenting clinicians. Finally, I want to conclude by saying that as we look into the future, our healthcare system and healthcare workers will only continue to get increasingly overloaded and to experience increasing burnout. Major events such as the COVID pandemic is already one example of this, but even beyond this, we're quickly approaching the 2030 problem, which refers to the year when the baby boomer generation is expected to reach senior age, and the ratio of caregivers available per senior is expected to drop precariously low. And so as we approach these scenarios, I think a major part of the solution will be these AI-infused technologies, where we can leverage the strengths of AI to provide much needed assistance, and in many cases also relief to clinicians and to augment their ability to deliver quality care to all patients. Last but not least, I'd like to acknowledge my wonderful group of students and postdocs who are driving all the research that I've discussed today. And I think we have a really great group of researchers who are all passionate about both methods development as well as direct healthcare applications. And with that, thank you.
Wow, Thank you, Serena. That was super fun. So we have a healthy list of questions here, and I want to revisit sort of both the beginning and the end of your talk. In the beginning of your talk, you said these striking statistics: 78% of physicians and 62% of nurses experience feelings of burnout, which leads to a 40% increase in life-threatening injuries. And then at the end of the talk, you said it's going to get even worse with the 2030 problem. In the middle of your talk, you outlined very cogent mechanisms for dealing with this, with AI across understanding clinical procedures, ambient intelligence in the hospital, and telemedicine at home. And I want to get into deeper questions in those three areas, but I also want to take a step back. How did we get to this situation in the first place with this amount of burnout and this lack of sort of this ratio of care providers to patients? Even before we get into AI, like, how did that happen? Is it unique to America? Is AI really the only solution here? Is this a bigger problem? How do I think about that?
Well, I think to start with, I think healthcare is also, just hard. It's complex. Patients are sick, and we're constantly trying to develop better and better ways to treat patients. And so I think it starts from that. But I think that on top of that, there are certainly many systemic issues as well. For example, let's say the difficulty of interacting with electronic health record systems that can contribute to the day-to-day experiences of physicians, and this can lead to some of these phenomena behind burnout. And so I think that there's both some of these, just the nature of healthcare itself. There are these just the natures of the job where I think here we can use AI in many ways to just help make executing these parts of the job more effective and more efficient. And then finally, there is that phenomenon related to the 2030 problem, whereas just we have a growing aging population, and that's a global phenomenon. And so at the same time, that ratio of healthcare workers for each aging person is decreasing. And so I think it's kind of the combination of all of these sorts of things.
They all add up to make a more difficult problem. Okay, and so another question from the audience, right? So, you kind of, throughout the framing of your talk, you referred to automated driving with different levels of automation, from 0 being no automation, 5 being the most automation. With respect to sort of automated vehicles, starting from the DARPA Grand Challenge, 20 years ago or so, it didn't work. And now on the street, I'm seeing what I presume to be automated vehicles. In the hospital setting, when do you think we'll sort of achieve that similar state of progress to where we're at with autonomous vehicles? Like, when is AI expected to be deployed on a global scale in hospitals? Is this a 0 to 5 year thing, a 5 to 10 year thing, or something more?
Yeah, so I think the really interesting thing about AI applications in healthcare is that there's such a broad range of possible applications. And you could imagine AI being used across many of the ways we talked about today, but even beyond that. And so I think that what we're going to see is a gradual increase in the use of AI in different ways, and maybe in some cases some very limited applications. Let's say watching for a particular type of error during one procedure, that even in the relatively near future we could already start to see AI having significant autonomy in that area, but others will take longer. And so I think it's going to be that sort of depending on the application and bit by bit building up this ecosystem of AI in healthcare. And I think that a lot of this is also going to depend on the nature of applications, right? So, areas where AI can be assistive, but it's not going to actually cause risk to the patient, right? For example, either using aggregate statistics, running in the background, always having a second check. These are application areas that I think there are areas that can start to be deployed even relatively soon, versus the ones where you imagine an AI kind of in making executive decision making about treatment for patients, that some of these may take quite a bit longer, especially if there's no human as a second check.
Right. Yeah. Excellent. So diving in a bit more to the sort of the meat of some of the issues in your talk, when you were talking about sort of the detection of tools and hands and actions in YouTube videos of surgeons, you showed very compelling statistics about what tools were used for what amount of time, or even sort of the jerkiness or lack thereof of the hand movements and how that assesses to skills. There's sort of two broad questions that I'm seeing here. The first one is really around how do you have you tried to surface that information back to the physicians so that they can kind of learn from how they sort of rank up with respect to their peers? And another question is, a lot of that work is about videos. So how important do you think a multimodal data analysis would be? For example, hearing what they're saying or the sound of the tools on the anatomy and so on.
Yeah, I think those are both great questions. So the first one, are we surfacing findings back up to surgeons? I think this is we're in the process of working on all of this. So maybe next time we'll have an update on that part. But I think that so far what I showed today was mostly the computer vision ability to produce discernments from the video. And I think to really look at some of these findings, it requires what we're doing now, which is this type of analysis at a much larger scale, and then being able to link that with certain types of either complications or levels of skill, and to have the quantity of data to be able to gain more insight into these findings. And so that's something that we're in the process of working on. For the second question, might multimodal data be helpful beyond just video in these cases? I think definitely. I think that you can imagine a video captures a lot of information, kind of the core part of what's happening, but certainly information just even about what's happening in the room, and beyond just the surgeries themselves, also information about the patient, right, or the patient trajectory through their care. I think all this information can be complementary to study different kinds of questions. For example, I could imagine data about what's happening in the room, even how the surgeons are interacting with each other, are useful for studying kind of the management of surgeries and across a team of clinicians in the room, whereas looking at a patient's full history in their health records, in addition to the surgical videos, can help with deeper analysis about the link to outcomes. So yeah, I think these are definitely interesting directions for future research.
There's just never enough time to do all the findings.
Exactly.
So another kind of group of questions that have very interestingly come up from clinicians and physicians are first of all, everyone's very grateful for your work. I think everyone is saying AI can really help us. That seems to be the consensus opinion. But the real question is, how do you choose of the myriad problems that physicians and clinicians face in the hospital, which ones to work on to sort of assist those people with AI? Like what makes a problem good for exploring an AI physician partnership? How do you choose?
So I think I guess I think about it in a couple of ways. The first is thinking about where, especially my expertise is coming from computer vision, where I think computer vision can potentially have the most impact. For example, surgery is, very much visual in nature, and same thing about, activities happening in hospital rooms. And so thinking about where this can have, I think is really driven by the types of technologies that I feel like we're able to build, as well as it kind of being at a sweet spot of both interesting technical challenges, where if we're able to unlock some of these technical capabilities, we can enable these applications, but it's not so far-fetched that we're going to always be staying in the realm of kind of research algorithms and never being able to deploy anything. And so I like to be working closely together with clinicians, where we can think about both building these algorithms, but also importantly working on them in real-world settings. And then I think that also ties to kind of the second part of just how I also like to think about research, is that across these different applications, if we actually think about some of the underlying methods challenges across them, well, there's actually broad methods questions that span across these, right? For example, if we're able to develop algorithms for interpreting video data with much more limited labels, much more efficiently, well, that can kind of, exponentiate our capabilities across multiple types of data. And this is also a common bottleneck across multiple types of data. And so I think that by thinking about these different types of challenges and what are common kind of technical questions that underlie them, I think for me, this is also a interesting way to think about the research problems that I want to pursue.
Great. And so maybe riffing off of that a little bit. So in the context of the ambient intelligence in the hospital, you started off showing us results from using depth sensors. And then you said, and I was struck wondering why depth sensors of all the kinds of things. And then you mentioned, you can use RGB, and you sort of hinted, well, there's privacy issues there. And there's a kind of a class of questions here, which are, what are the actual challenges to implementation? So from taking a research algorithm to actually getting it to work in a hospital to affect positive outcomes for both physicians and patients that you've sort of encountered in your work thus far. And how have you overcome them or not? And then a follow-up, a sort of a related question to that is, you mentioned a few hospitals in which you piloted these things. How will the algorithms you've come up with thus far generalize to other hospital settings? Or will that be a different algorithmic challenge, or are you less concerned about that? So sorry, there's a lot in there, and I'm happy to.
I'll try to remember all of it. So the first part on just implementation of these sorts of things, I think the most absolutely critical part of this is a really tight partnership and collaborative relationship between all the parties involved. And that's, in our cases, that's both, computer science researchers, but also clinicians, that's nurses, that's other, people working at the hospital across different types of roles. And I think what's most important, and because these are all technologies that, can have a dramatic impact and are disruptive, but at the same time, there's not much precedent, right? So I think that when we're in that kind of a realm, it's just extremely important to, one, have the buy-in of everyone involved, but two, to think about these sorts of deployment questions with everyone, right? Certainly, let's say the nurses or the hospital executives are all going to be thinking about different questions and aspects that I wouldn't have naturally been aware of, and so thinking about all these things to design the implementation together. And so I think that's really the key part. And then for your second question about generalizability, pilot. So we implemented these at a couple pilot hospitals. I think that it was, actually, we were fortunate to be able to have 2 partner hospitals because we could test some amount of generalizability. And we did, for example, in the hand hygiene case, do a test of generalization, and we sort of found what would be, expected, where the algorithm from one hospital transferred to the next still worked reasonably well, but got, a bit of a decrease in accuracy. And then if we fine tune it on some data from the second hospital, the overall performance then ended up better than either hospital alone. And so that's, I think, what would be expected with 2 hospitals. But certainly, I think generalizability is a big thing of interest. I would say this is a case where there's a lot of research opportunity to think about how we can obtain this generalizability efficiently, without having to say go to 50 or 100 hospitals, because data isn't as easily collected in this way, the same way as it might be with other types of computer vision tasks. And so I think that in this case, actually, it's similar to some other types of cases where some of the constraints that you might have, in healthcare, as actually the source of really interesting technical questions that you might think about. Right? How do you develop generalizable algorithms without just sort of brute force throwing tons of data at it from all different kinds of institutions?
I see. Okay, so there's so many good questions on the chat. I'm very sorry I wasn't able to get to all of them. If you have 30 seconds, the highest rated question here is, how do we prevent EHR-induced burnout? The advent of EHR was meant to ease physician workload. However, it made physicians spend more time on their computers, and you didn't quite talk about that, but I'm wondering if you're working on that as well.
So I think that question in general is a little bit more systemic and above my pay grade a little bit. But I think that certainly on the question of EHR based, burnout specifically, I think that there's, many more systemic issues related to, how these systems were designed, the incentives, and how they're being used now. But I think that, kind of as a complementary track of thinking about things, I think that, AI does have the potential to still assist with this, right? That they can make interfacing with EHR easier. You can imagine, automated documentation, right, at one extreme of this. And so, I think we'd like to fix the systemic issues regardless, but I think AI can still provide, useful ways to enhance the clinician experience as well.
So exciting, so much work to do, and thank you so much for presenting your amazing research, and thank you audience for tuning in. And I guess we can all imagine a virtual round of applause of about 350 folks. And thank you so much, Serena, and we'll see you HAI audience next week. And Serena, I'll see you soon.
It was great to be here, and thanks for having me.
Thanks. Bye-bye, everyone.